Welcome everyone to the webinar. We are excited to be presenting this webinar, and to get us started, Carla, please go ahead.
Welcome to Soils, the Foundation for Life, a K-12 educators webinar. This webinar is sponsored by the Soil Science Society of America and the National Earth Science Teachers Association. The National Earth Science Teachers Association is a member-run nonprofit supporting the teachers of earth and space science at all levels and helping to fuel the passion for earth and beyond. We facilitate excellence and in teaching, and we serve a diverse population of learners both in formal and in informal settings. We offer online resources, professional development, and a quarterly reviewed journal, The Earth Scientist, plus monthly e-news to our members. We also have an internet presence. And we encourage you to visit our website at nestanet.org or join our Facebook group or follow us on Twitter. And with that, I will pass it over to the facilitators.
Thank you, Carla, for the welcome and for hosting the webinar. On behalf of the Soil Science Society of America, we're excited to present this webinar, which has been one of our goals since we started developing K-12 resources actually 12 years ago. I'm Susan Chapman with SSSA and serve as the liaison to our K-12 Outreach Committee that works with our scientists to review and develop resources for you. Along with me is Missy Holzer, our committee chair and a science teacher at Chatham High School in New Jersey. The content of the webinar connects not only with NGSS Earth and Space Science core ideas, but life science and physical science core ideas as well. There's just a few notes before we begin. You're welcome to ask questions via the chat box at the lower right of your screen. There are two options for posting the question or comment: to all audience members or just to the organizer myself. So be sure to select either option from the drop-down in the chat section. To keep the flow of the webinar, we'll answer questions at the end of the presentation. After the webinar, you'll receive a feedback survey. Please take a few minutes to give us your thoughts. This is our inaugural webinar, so all feedback is welcome and will help us to build our resources for you. So as a quick overview, the webinar will have 4 sections, and here are the folks that you'll hear from during our presentation, and they will be introducing themselves as they start their sections. To keep our time focused, we have posted their brief bios on the webinar web page. So first, Clay Robinson will provide you with an overview of soils. Second, David Linbow will talk about the 5 factors of soil formation, better known as CLORPT. Third, we'll hear from Wally Adewunmi on the characteristics of soil. Fourth, Rachel Legge will discuss a bit about soil fertility and what that means. Finally, we'll wrap up with a short overview of some great soils resources and have time for Q&A. So with that, I will turn it over to Clay Robinson to get us started. And Clay, you're live.
There we go. It always works better if I'm not muted. My name is Clay Robinson. I'm a soil scientist and have been for many years. Many people, though, especially in the K-12 audience, know me better as Dr. Dirt. And you can do some search on that and find my internet presence in YouTube and Instagram and all of those kinds of things. So what is soil? This is always a great question, and one of the ones that we have to face all the time and deal with. So first, soil is the foundation for all terrestrial ecosystems. And because it's always underfoot, it's almost always overlooked. And too often then it's also underappreciated. So we have our nice pastoral scene that's supporting our terrestrial ecosystems there. Soil is the intersection of all these other spheres on Earth. So we all know about the atmosphere, the gases that we breathe and use and even expel. Then we know about the lithosphere. This is the where we talk about geology and the minerals and the rocks and the sediments. The hydrosphere, that's where our water and where it exists on Earth, in Earth, and the whole hydrologic cycle. The biosphere you probably know well with our plants and animals of all sizes and their byproducts. And the term that you may not yet be familiar with is the pedosphere. This is the soil, and this is the part where all of these others intersect because there's air in soil. The soil has living and dead organic materials in it. There's water in the soil, and the soil itself is composed of mineral particles. Now, just thinking about this, going from a Venn diagram into a couple of pictures of some soils where we dig a hole, we call these soil profiles, and then we look and describe what we observe. Well, you can see that up here at the top, we have our biosphere, some living plant material, and then we move into this area where we have the soil, our pedosphere. In this case, we also can see the lithosphere. We can see those rocks that this soil is forming in, and Dave will tell you more about those later. In this one, we can see that there's water in the bottom of that pit. So we've got a water table. So the water is not only existing in the pores in the soil, but there's enough water that it flows out into that pit if you dig a hole that's deep enough. So there we have our five spheres intersecting in the soil. So again, what is soil? Well, first and foremost, it is not dirt. Dirt is what's under your fingernails, on the carpet, or on that set of dirty boots you can see over on the right side. Soil is a natural resource, and it's slowly renewable at best, and in some places it's probably not renewable at all. And David will talk to you again about that when he's talking about climate and other factors that can affect the formation of soil. Soil is diverse. It has a lot of different types of minerals in it. It's heterogeneous. And again, that's because you've got all sorts of different things in it, different types of living organisms, different types of sizes of particles, different types of minerals. So the whole thing, the pores in the soil are different sizes. And soil is dynamic. It's always changing. As plant roots grow in it, they change it. You walk on it, it changes. It gets wet and it dries, it changes. Plants take up nutrients. Things are changing in the soil all the time. Soil supports life, and those include from the very smallest scale of things you cannot see, like a bacteria, all the way up through the animals, some that live in the soil, others that live on the soil, to the largest living organisms on the plant, our giant redwoods and sequoia trees. Soil is important in this hydrologic cycle that we mentioned earlier because the water is moving through that cycle, and part of that cycle is in the soil. And if it goes through the soil, it can either improve the water quality as the organisms living in the soil can clean the water, or if things are not managed well, sometimes those nutrients can get into the water and causes problems. Soil is a building media. We use it for roads and buildings. We've used it for art and culture for years, generations, and millennia. And if you do a quick online search, you can find easily more than 15 definitions. Is there soil on the moon or other planets? Well, up until recently, I would have said no, because we said that soil is a terrestrial material. But the Soil Science Society of America changed the definition of soil to allow material on the surface of other planets to be considered soil, even though they don't have things growing in them and they don't have water in it. We've had a soil scientist working with NASA for years on the Mars rover project. Soil is an applied science. It uses chemistry, how things are made, physics, how things move and work, biology, how things live and grow, the hydrology, we've mentioned that, how these systems, the water is cycling through the soil atmosphere system, ecology, how all of these other systems and things affect the plants and animal communities, and then the geology of how those minerals affect the soil properties. Soil forms from the surface downward through a series of processes: additions, translocations, transformations, and losses. And we'll talk about each of those in a little bit more detail here. So additions are those things that are added to the soil. Most commonly, those things come in from the surface. Rain will bring in water, and the water comes with some salts and other things that are captured in those little raindrops, or things wash onto the soil. The water moves into the soil, and as it moves in, it brings things with it. Plants grow on the surface, and then they die and they decompose, or animals go across the surface and they eat stuff and they excrete waste, and those wastes die or decompose. And as they do, you notice that the surface layer of the soil is darker. That's because things are being added. And in this case, it's organic material, organic matter. Translocations, that's where things are moving downward in our soil profile. Things like soil particles of certain size, particularly clays, minerals, various sorts, iron, chief among those. And then organic matter can move down through the soil profile. So we've got all sorts of things that can move. So we've added stuff, we've translocated stuff. Here's some more examples of translocation and also of the transformations when things change. You can see that this soil changes color as you go down. Part of that color change is due to organic matter moving to a point and then stopping moving, but also this mineral here, calcium carbonate, that's being carried down through the soil. It reaches this point, the water doesn't go any deeper, and so that calcium carbonate accumulates at that depth. And on this size, we see another type of transformation where minerals are being changed, and this particularly deals with iron, as you see colors of kind of orange or yellow there. Iron that is oxidized is bright colors like oranges and reds and yellows, and when it's reduced, you get these dull colors, often grays or sometimes blacks. So these changes are happening from the precipitation events over here to the oxidation reduction events here that are changing the chemical nature of the minerals that are there. Losses is another one of these formation processes. And so in one case on the left, you see where almost all the coatings have been washed off of these particles. And so what we're seeing now is the individual particles, in this case probably of silt, that are left after all the organic matter and iron has been washed off. We also know about erosion. Here's a picture from the Dust Bowl, but we could easily find pictures more recently of wind erosion events. And then on the far left or far right over here, we have a picture of some water erosion, and that's happened in this past year near where I live in Illinois. Another thing, people are responsible for additions, and anytime we add things like fertilizer to the surface, we are adding material to the soil. And as a summary for that part, again, we've got additions, we've got losses, we've got translocations, and we've got transformations. And when we get to the end, we'll give you some more ideas about those activities that are available. But in this case, watch for one of these red stars, because it's going to tell you that something is available for you on that topic. So we have a poll question now. The question is, what fraction of the Earth's land is suitable for agriculture? So the poll has come up now. You have an option of 1/4, 1/8, or 1/32. So take a couple of seconds here and make your choices. And then we'll see. And when Susan looks like most of the people have responded, go ahead and close the poll and show us the results. If we started I'll go back at kind of at the beginning. We've got something that talks about the apple as planet Earth. And as we look at that, most of the Earth's surface is water. And then there we go down. And most people that are on here got that number right, because when we look at the soil, 75% roughly is water, leaving a quarter. Of that, about half is polar ice caps and high mountain ranges. We can't use it to produce crops, food and fiber, feed, clothe, and shelter all the people on the planet. Of the eighth that left, on 3/4 of it is too hot, too cold, too wet, too dry, or too steep, or too shallow to be used for growing crops. And this that leaves us with a fourth of a half of a fourth, so 1/32 of the Earth's surface is usable for growing crops or for agriculture. And this word arable, that's what that word means. It means it's usable for agricultural purposes. There we go. So soils are diverse, mentioned that earlier. And as we look here, you can see, we won't go into detail about all these soil orders, but soil scientists have developed in the U.S. have developed a system of the classifying soils into different groups based on their properties. And as you look at the globe here, you can see that there are color patterns that exist. The green soils that you show on here, typically those that are forming under grasslands. And we can follow different features of these, but David Linbow is going to talk to us about that in greater detail as he talks to us about the factors of soil formation. And so,
All right.
Dave, I think it should be yours now.
As soon as I get control, we'll move forward. So as Clay said, when you look at the pattern and look at all of the regions and all the soils that are on the Earth, you notice that there's a lot of differences. And the big question is, what makes them different? And as soon as I get control, this is one of the, let's see. There we go. So what we're going to talk about is the soil from CLORT. And I do work for USDA, work for the federal government. We love our acronyms. I'd like to say I came up with this one, but I did not. This acronym has been around for a while. And what it relates to are the factors of formation, or why soils look different. And it boils down, these factors are climate, organisms, relief, parent material, and time, or CLORT. So as we look at them, the soil forms through the interaction of these factors. No one is more important than the other. They all work together to give us the soil that we see. So let's start with climate. Temperature and rainfall has an effect everywhere. Think of it in terms of what temperature can do. It relates to plant growth, the biology, the evapotranspiration, which is the evaporation of water as well as the water moving through the plants and out through the plants. Chemical reactions speed up as temperature speeds up. There are physical reactions, freeze, thaw. Precipitation, as Clay talked about, brings stuff in, dissolves material. Plants grow different depending on the amount of precipitation. So the microbiology, the bacteria grow different. And there's translocations, transformations, and erosion, all related to precipitation. And if we think about it, we can break precipitation temperature relations into four things: hot, dry, hot, wet, or cold, wet. And different areas have different relationships. And then there's the microclimate, which way the slope is facing, how much air drains through it, how high the site is. So if we think about that, we get to a poll question. Where do you think in the world how the soils, where do they have the highest amount of organic matter? So hot, dry, hot, wet, or cold, wet. Take a minute, vote on it, and let's see how you did. You guys didn't think you were going to be having a test, did you? So a couple more seconds. Let's see how folks have done. All right, so as soon as folks, we've got the majority in, let's see what the results look like. So a lot of you put down what normally people do is they think hot, wet. They think that it's the tropics. But in reality, most of the organic matter that you find in the earth is in the cold, wet climate, the tundra. And if you think about it right now, there's a lot of concern over that area warming up and that organic matter actually decomposing? So the answer is the cold, wet areas. More biological activity, more growth, but the cold preserves that organic matter. So as we move on, you can see, let me back up a little bit. You can see some of the climatic differences and just the way the soils look. In the warm, humid areas, we have thicker surface layers, more layers, more visible layers present, and the soil develops differently than it does in the warm, dry area where we don't see as much development. So then moving on to organisms, the biology, the vegetation, what we see is how organisms can affect us, the plants, the animals, the microorganisms. And in reality, it's the microorganisms that really give us a lot of the differences that we see in the soil. It holds it together, it mitigates or changes, and a lot of the chemical reactions are because of the bacteria and the fungi in our soil. So if we look at it, we can have turbation. The critters move things around with rabbit warrens, anthills, crayfish, and then tree throw, where trees fall over and mix the soil. All of these tend to make the soil more homogeneous. It removes the layering that we see in the soil of the horizons. Okay. And we can also see that vegetation has an effect, from grassland, thick, dark surfaces, to deciduous vegetation, where we do have some organic matter there, but a lot of that organic matter cycles very quickly. But then if you look at coniferous vegetation, the water moving through the leaf litter is very acidic, so it creates this bleached layer within the soil. So vegetation can also have a huge effect. Relief, where are you on the landscape? The topography, high, low, etc. So if we think of it, topography, relief could be the degree of slope, which relates to how stable that site is, and the location on the slope, how much water is present, where is the water table on that slope. Quickly, you can measure slope by taking a level and a ruler, lifting it up to where the ruler is level, measuring at the far end what the distance is, and doing a quick calculation. So if my ruler was 100 centimeters and I had to raise it 5 centimeters to get it level, I can quickly calculate the slope, and in this case, the slope is 5%. And we do have an activity on this so that you can see how to do this in a classroom. Slope also relates to the profile thickness, where the organic matter is, how thick the A horizon, the surface layer is, the wetness, the color, how well expressed those individual layers are, the chemistry and the temperature. All of these are affected by the relief as well. So if you look at it in a landscape at the summit, we have a fairly deep soil, well-developed shoulder, because there may have been some erosion, the soil's a little thinner. On the back slope, more water moves through it, so we start to see some evidence of leaching and movement of material. Foot slope, things start to get a little bit yellower. You're moving from reds to yellows, and then when you get down to the foot slope, you see this gray color occurring because this is a wetter soil, so there's more water down at the toe slope. It's a less well-drained or a wetter profile. Move on to parent materials. And yes, soils have parents too. Parent materials can be broken into 3 basic groups: transported, bedrock or residual, and organic material. And this diagram, rather complicated, but there's a lot to it to understand. We can start with rocks. Rocks and soil that develops directly from the bedrock is called residual material. If the rock moves, we then have sediment. We can also have plants in particularly wet areas that give us the organic parent materials. Let's go back and look at the sediments. So sediments can be transported, and it all depends on what transported them, whether it's and where it's deposited, whether it's in lakes or streams, oceans. Gravity transported would be colluvial, landslides. Material moved by wind is aeolian. Material moved by ice, till, and outwash. And some of these can move back and forth, and you can get some material that's transported first by ice and then by wind. So the parent material can be relatively complicated. Okay? So if we think what organic material looks like, a lot of times we find them in marshy areas, low-lying areas that are very wet. Thick, dark material is typical of organic parent material. Residual parent material looks like rock. And if you look at this profile right in the middle here, that lower section, that is saprolite, which is highly weathered rock. It still looks like the rock, but it no longer feels like it. You can dig through it with a shovel very easily, even though it still looks like the rock. Sometimes the rock doesn't decompose as much and is still hard, but these are all residual parent materials. We then have transported materials, materials that have moved and then continued to weather. This diagram shows all the various types of parent material that could be moved and what they could be moved from, and they can occur all across the landscapes. So water transported to ice transported, common everywhere. Wherever you go, you can find these transported materials. Wind transported, I did want to spend a little more time on. Clay talked about the effect of the Dust Bowl, and this slide down at the lower left is a modern dust storm. At the top left, though, we see dust coming off of Africa, moving into the atmosphere. So wind is not necessarily a local event. It could be a global event. Some of the material is transported. We also know that this loess material, this wind-transported material, is very important to where there are some of the more fertile areas. Some of the best soils in the world are in these areas where we have a lot of wind-transported or loess materials. And then finally, time. Time is a degree of formation. It's not an absolute. So if we go back to our hot, dry, hot, wet, and cold, wet, in some areas we have slower development, in other areas fast. Remember, hot, wet areas, the rapid decomposition, that's why we don't have a lot of organic matter, but it's more bacteria moving or working, more biology, so you have quicker development of that soil. So time in soil formation is relative, it's not absolute. If we look at two different soils, more on an absolute scale, few horizons is a young soil, older, have more horizons, more layers, more definition. Okay? So a poll question, how long does it take for an inch of soil to form? So I want you to think about that. The poll should be coming up. Is it 5 years, 50 years, 100 years, or 1,000 years? So the question again, how long does it take for an inch of soil to form? So take a few minutes on that, see what we can come up with. All right, so the answers that we got, good. Most people were in the right ballpark, between 100 and 500 years. So anybody that answered 100 to 1,000, you're in the right ballpark. So most of you got it. It takes a long time for that inch of soil to form. But then think about how quickly, if you don't have good management practices, how quickly you can lose that inch of topsoil. That's, may have taken 500 to 1,000 years to form, and it can be lost overnight. So again, pretty important to maintain and manage our soils well. So if we think about the general time sequence, again, start at 0. You just have the parent material. By the time you hit 50,000 years, Ka stands for thousands of years, you get a much more well-developed, thicker profile to look at. So deeper soils over time. So factors of formation, again, our climate, if I can get my mouse to work here, organisms, relief, parent material, and time, or clorped. These factors of formation make the soil look the way that it does. So next, what we're going to talk about, Wally will be discussing not how the soil forms, but what are some of the properties of the soil that you can look at, measure, and describe. So with that, I will turn it over to Wally.
Thank you, Dave. All right. Well, in a few minutes, we're going to be considering the four physical characteristics of soil. And let's see if I can change my slides here. Okay. All right, there we go. So we're going to consider four characteristics of soil. So texture, soil color, soil structure, and soil profile. These four there are more characteristics than these four, but we're going to talk about four today. And these characteristics are used in describing soils, just like the two speakers before me just told you. The most obvious one to that people notice is color. And just like you see there, we're all familiar with M&Ms. And just like M&Ms, soil is colorful too. And just take a look at these four pictures. I think you've seen something like this when Dave was speaking. In these pictures, we can see different colors, yellow, red, or brown, bleached color. We can see dark color. Well, what does all these colors, what do they mean? These colors in themselves have little to do with the behavior of soils, but they give us a lot of information. For one, these colors are important when it comes to classifying soil and interpreting soils. Soils indeed do have identity, and one of those items that we use to identify them is soil color. Now, I think the speakers before me mentioned these colors are the result of different processes that's been going on in the soil, like the yellow or light colors. Those come from oxidized minerals like iron or elements like iron. And dark colors, like you see on the right, that comes from reduced iron compounds, or in some cases, manganese manganese as an element and its compounds do produce really, really dark color. Now, what do these colors tell us? We associate bright colors with a well-drained soil, and the dark colors with poorly drained soils. And and I think as we go on, you're going to see some of these, some of the reasons why this is so. Now, we all know how to observe soil, but when it comes to, to observe colors, but when it comes to describing it, it is subjective. We can say it's kind of yellowish, red. We have our descriptions. So for soil scientists, we use a standard reference called Monsoil Color System, and the book looks like this with a ring binder, and there are many pages in it reflecting different colors. Now, these colors are a combination of three factors: the hue, which describes the dominant wavelength of light that's reflected; chroma, which describes the relative strength of that hue; and value, which describes the lightness or the darkness of the color. And after this presentation, if you go to our website, which we're going to give you at the end, there's an activity that you can do, and you're going to get more information on this short description of colors. Now let's move on to another item, another characteristics of soil, and that is soil texture. Well, every soil, every mineral portion of soil, excluding the organic material, excluding air and water, all those that were talked about before, the mineral portion of soil can be separated into three size particles. And these particles are based on the diameter of the particle. And as some of us, as we all know from chemistry class, finer materials have a larger surface area and they're very reactive. But in this section, we're talking about physical characteristics only. So to put this in perspective for you, think of a sand particle as a basketball and a silt particle as a golf ball, and think of the clay particle as a marble. And you can get a sense of the mixture that we have in the soil. Now, if you were to put this in a trash barrel and mix it together, or just put them in there, there is space between each of these, between the basketballs, between the golf balls, between the marbles of the mixture. Those spaces are what we refer to as void or pore space. Those are very important, and we're going to talk about that when we get to one of the other characteristics. Now, soil scientists can estimate soil texture by feel when we're in the field. And we do that, as you see in the picture, by holding a moist soil between two fingers. And you can feel whether it's smooth or grainy or in between. In the laboratory, we have a more quantitative way of determining that. There is an elaborate procedure for that. And so we do that in the lab. But there is an easy way that you can do it. And we have an activity for you on where you can do it yourself in your school. It's a jar test, more or less. And as you see in this picture here, you can use clear bottle like a mason jar. And thinking about it, you can even use a water bottle because it's clear and you can see the contents inside it. And so if you go to our website, you can see this activity. All you need is some soil from your schoolyard or from home. If you want to get the students involved, they bring soil from their homes. You need some water, and you're ready to go. At the end, you're going to have something that looks like this. You're going to see the different fractions of that soil. Now, one quick thing about soil. We've all seen the picture on the left, or something that looks like it. What's an ideal soil? Well, an ideal soil, what we like to call an ideal soil, is a loam or loamy soil. Now, this type of soil does not have 33% sand or 33% clay and 33% silt, not at all. But it has all three fractions of all these three fractions in enough quantities that it affects the behavior of that soil. That's a loamy soil. All right, let's move on to another characteristic of soil, and that is soil structure. Well, this is, one of the things that we know that we've observed is that soil occurs in clumps or clod or aggregate. If you were to dig, you'll find out the soil doesn't come out loose. It comes out in clumps. Well, these clumps consist of those individual particles that we just talked about, sand, silt, and clay. The arrangement of these particles is what we have in those clumps, and the arrangement of the clods or aggregates is what we refer to as soil structure. It gives soil some structure. Now, you might wonder, or you might have a question, how does the soil get its structure? Well, it's a naturally occurring process, which includes alternating freezing and thawing, as Dave just described in the process of soil formation. This includes wetting and drying, penetration of plant roots, burrowing by worms, insects, and animals, and exudates or things that plant roots release into the soil. And lest I forget, microbial decay of plants and animals. All these together affect the arrangement of particles. Remember, we said earlier that the soil is made up of mineral particles, minerals, organic materials, air, and water. So all these combined to give soil its structure. So we talk of soil structure in terms of granular. These are terms that we use to describe soil that's easy to work with. An example of this is what you're going to find in a topsoil, which I'm going to discuss later. We also describe soil structure as being blocky, as you can see in this picture. It naturally comes out in clumps that looks subangular blocky. Additionally, we talk of soil structure in terms of being prismatic or columnar, as you can see both in the illustration and the picture. Or it can also be platy, and I think that's self-evident. You can see that. It's arranged, it's stacked up like plates. And as Dave said earlier, this is soil, even though it may look like rocks. It's not rocks at all. Well, maybe this is a shocker, that some soils actually do not have structure. We refer to them as structureless soils. An illustration of this are single grain soils. In this picture here, if you were to be on this field, you can literally scoop this soil with your hand and it will go through your fingers. On the right, this is a soil that just exists massively in place and has no particular structure to it. So at this point, let's take another poll question. And the question is, which of these soil structures that you just saw will allow water to flow faster through the soil? So take a few seconds and answer that. All right. So we're going to see the answers in a few minutes. Well, it shouldn't take minutes, really. All right, here we go. And I think everybody seems to be in line here. You guys are great. It's granular, as you can see. At you. So this is an illustration of that question. This is water flowing through at least four of those soil structures. And you are right that it's granular. That has enough pore space, enough void to allow water to flow faster and quickly too. Now, just in the same way that water flows through these pore spaces, that's the same way that roots find ways to penetrate this soil and to grow. All right, let's quickly go to the last soil characteristic, and that is the soil profile. Now, when you dig into the soil, if you dig enough, well, not a hole where you're going to put a pole or something or some tomato plant, but if you dig enough to see the soil from top to bottom, this is what you're going to see, something that looks like this. It's a three-dimensional view of soil. And Dave spoke a bit about all these layers. The key things I want to mention to you is that the top layer is the organic layer. It has organic materials from plant and animal tissue in various states of decomposition. Well, because that is sitting on the mineral fraction of soil, as it becomes, when it becomes soluble, it moves down into that mineral section. It influences the ease with which that soil can be walked. That is what we usually call topsoil. That's what we all like to have. And as you can see, the color is dark from that organic matter. And that's what people try to imitate when they produce topsoil for us in bags to buy. They want us to buy something that looks like this. And I think Dave has talked about different layers of soil. And Clay also said that, how things move up and down in the soil layer. And of course, we get down to sea horizon. This is the material that's weathering right there in place, the parent material. And so these characteristics, as I just said, are very important. We use them for describing soil. Well, before I move on to that, we have an activity for you on our website that you can also do. It's a simple one. You take a filter paper or simply a paper, Elmer glue, and some soil material, dry soil material, and you can make a soil profile like this in class using different colored soil. And this is a very nice activity for all grades, maybe more for the younger children than for the high school level, but it's a very good hands-on activity. And lastly, before I hand over to Rachel, why are these soil characteristics important? Well, in addition to classification and identification of soils, they are pretty important when it comes to the environment, because as you answered in the poll question, water movement into the soil, within the soil, and water storage for plants depends on these characteristics. Soil erosion is also influenced by these characteristics. If the soil is loose or it's easier to be eroded by water or even by wind for that matter. And it's also important for heat transfer, for the ease of tillage, and for root growth. So at this point, I'm going to hand over to Rachel, who is going to tell us about soil fertility.
All right, hello everyone. Now we're going to transition into soil fertility, and we're going to learn how we can apply these soil basics and their interaction between soils and crops. So just as we rely on food to provide ourselves with nutrients for our bodies, soil provides the same nutrients to crops. Soil is ultimately the basis for all of our food, fiber, and pharmaceuticals because of this important relationship between soils and crops. So now let's talk about the essential plant nutrients. Just as we need nutrients to survive, plants require 17 different nutrients in order to live. These are all listed on your screen to the left, and we also listed 3 beneficial nutrients which help plants survive. On the right, you can see a barrel. This barrel has staves on the sides, and each barrel stave has a different nutrient that is necessary for plant growth. As we can see, the water here represents the yield potential, and that yield potential is limited by the staves that are the shortest. The barrel can only hold as much water as the shortest stave. In this case, the K, or the potassium, is the shortest stave, so that's the limiting factor. This relates to Liebig's law of the minimum, which was a German scientist that figured out that plants can only yield as much as the limiting nutrient. So even if we provided more nitrogen or boron in this case, the plant wouldn't be able to grow anymore because that potassium is the lowest nutrients available. Next, we're going to talk about how we can visually make observations to determine characteristics of soil fertility. So on the left here, we can see a corn plant that has yellow leaf margins, and that's what we as scientists like to call marginal chlorosis, because there's chlorosis, which is the lack of chlorophyll on the margins of the leaves. So in this case, the plant does not have enough nitrogen, which means there's either not enough nitrogen in the soil or the nitrogen that is in the soil isn't available to that plant. And we'll talk about that a little bit later. On the right, we can also see that too much might not be a good thing. In this case, too much phosphorus prevented that corn plant from taking up zinc and other important nutrients. Just like in our bodies, if we get sick, we don't always look very great. If we keep an eye on our plants, we can see if those plants are getting the right nutrients, and maybe that means there's something going on in our soil. Now that we know about our nutrients and what nutrients the plants and soil need, let's talk about the nutrient cycle. Where does this nutrients come from and how is it recycled? Well, we'll start on the left here with the inputs. The inputs can either be biological or natural, such as biological nitrogen fixation, where the little organisms within the soil convert the nitrogen gas in the air into usable nitrogen. We can also use inputs such as fertilizer, whether that's manure or synthetic fertilizer, lime, organic material, and also atmospheric decomposition. So once those nutrients are in the system, plants can only take up the nutrients in the forms that they need. Once that nutrient is in the plant, it eventually will be harvested, and farmers take off some of that nutrients in the form of the crops, such as corn kernels or soybeans, and whatever is left of that plant that the farmers don't take out of the field is left as plant residues. Those plant residues eventually break down and release that nutrients back into the soil that eventually can go back and be recycled, or it can be lost. The ways that nutrients can be lost is to the atmosphere as gas or through erosion, leaching, and surface runoff like we talked about earlier. Now, we talked about the nutrients and where it comes from, but how does it move through the soil, and how does the plant actually get it into the system? We like to categorize nutrients into two different categories. One is mobile and one is immobile. On the left here, we see the mobile nutrients, which, to be honest, there isn't very many mobile nutrients, and those nutrients can flow easily through pore spaces in the soil, and roots don't need to be right next to that nutrient in order to get to it. On the right, we see immobile nutrients, which you can see there's quite a few more that are immobile, and those nutrients can only be taken up if it's fairly close to the root system. Finally, we're going to talk about nutrient management. So it's very obvious that soils and crops have a great relationship and they are interdependent, but we as people also need to manage these systems. When you think about the decisions that farmers and scientists have to make, it's quite a complicated equation. They need to think about the 4 R's when they make decisions for the operations. That includes the right time, the right source, the right rate, and the right place. Now let's go through those a little bit and talk about what the decisions might be. When we talk about the right time, we can think about the time of the year. As we see on the left, it's before there's anything growing after the corn was harvested, and on the right, it's after the soybeans are coming up. We can also think of the time of the day. In the morning, it might be more calm outside, but if it's in the middle of the day, it's going to be warmer, sunnier, and possibly more windy. Next is the right source. Farmers and scientists need to think about what source of nutrients is going to have the best ratio for what the crops and soil need. Third is the right rate. How much of that nutrients does the soil and crops need in order to meet its optimum yield? Finally is the right place. Where can we apply this nutrients to make the most sense both economically and for yield potential? Next, I'm going to hand it over to Susan Chapman, and she's going to go through some more of our soil science resources.
Wonderful. Thanks, Rachel. So I wanted to give all of you a little bit more information about where you can find a lot of the great resources that our soil scientists have put together that you can use in your classroom. So first of all, our main resource for you is www.soilsforteachers.org. And you can see when you go to that site, there'll be a lot of navigation. There'll be information on soil basics, a lot of different soil subjects. I'm sorry, let me back up. The homepage, you will find Ask a Soil Scientist over here, which we'll touch on in a minute. A glossary, we've got a store with books and the ever popular I Heart Soil stickers. The soil subjects that I referenced have a lot on the basics, the formation that we heard about, and then dig more into that biology, chem, fertility, mineralogy, physics, and forensics. We can also go to Around the World, and you can see drop down for state soil booklets. And right now we are about 85% complete developing a state soil booklet for every state. And when you go to this page, if you hover over your state, if it is outlined in red, it's ready for your use. We also have a land and people section, which connects soil to a lot of other obvious things besides just the science. We also have our lessons and activities. So we have gone out, found a lot of great resources in addition to our resources. Soil scientists have reviewed them. We have categorized them by topic and by grade level. And then I mentioned the Ask a Soil Scientist program, where you and your students can pose a question around a lot of different subject matter areas. And then you as teachers can also request a classroom visit. And we will work to try to find a soil scientist to come in. We can't always guarantee it, depending on the location and the time of year. But our members love to come in and talk to you about soils. We also have a section on our soil science website, www.soils.org/IYS. 2015 was the International Year of Soils. Yes, soils had its own year. It was actually a United Nations declared official year. We developed monthly videos. We developed activities that you can use in your classrooms for each of those months, and they all had different themes. So then to pull all of the materials together that you heard about today, all of the activity alerts reside on soilsforteachers.org/webinar. It's also where we will be posting an archived version of this webinar because we're recording it. And I've also listed all of the different resources for you. So on that note, we want to thank you for attending, and we do have time for some questions. About 3 or 4 minutes for them. So please go ahead and post your questions. And we do actually have a couple that have already come in. So if I can go ahead and have all of the presenters just jump in. One question that came in is, how do scientists determine the parent material of soil?
I guess I'll take that. This is Dave Linbo. A lot of times we go back and we look at geologic maps. So the geologists map what's deeper down than what soil scientists map. So a lot of times we work with the geologists to find out what the parent material is, the material deeper underground is. But we also have to look at the material to confirm that the geologists were indeed correct. So it's a combination of using material that's already out there from geologists, as well as looking at the characteristics of the soil to determine what that parent material is.
Great, thank you, Dave. I think this is a question then for Clay. The question was, the current arable land is 1/32 of the earth, as we learned. Is there any chance this could increase or decrease over time, and how?
Well, one of the greatest challenges we face is a changing climate and that affects the amount of land that we can use. For instance, for all of you chocolate lovers, the band of elevation and latitude where you can grow cocoa is decreasing. It's being diminished as the earth warms. And so rainfall patterns may change. It's more likely in some areas we'll lose soil to its productivity. In some other areas we may be able to gain a little bit if they pick up in rainfall. So it's going to be determined a lot in the next few decades as the climate changes, as rainfall patterns shift. So all in all, we're probably looking at a net zero difference in those changes.
Thank you, Clay. We do have several other questions that have come in, but I want to be respectful of everyone's time. So what we're going to do is have those questions answered by our presenters, and we will post them on the web page. That's www.soilsforteachers.org/webinar. So at this time, on behalf of the presenters, our entire Soil Science Society of America membership, we want to thank you all for attending, and please watch for the very short survey that we're going to send you. Be sure to visit the website for all of the great resources, and please feel free to contact us at membership@soils.org if you have any other questions. And on that note, thank you and have a great evening.